Elastic collisions. In an elastic collision, two objects collide and bounce off each other, as shown below. Here is before, here is after. And both momentum and kinetic energy are conserved. A prime symbol, right here, indicates the object's velocity after the collision. So VA, here's your initial velocity, VA prime is after the collision. This will give us two simultaneous equations to solve to predict their motion after the collision. Here's our two equations: conservation of momentum, conservation of kinetic energy. Substitute in the value for momentum, which is mv, and kinetic energy, which is 1/2 mv squared. And A and B, the subscripts, represent the two different objects. Since both of these equations describe the motion of the same system, they must both be true. Hence, they can be solved as simultaneous equations, or system of equations. Stand by for some algebra. We'll start with the conservation of momentum. Here's our equation from the previous slide, and what we're going to do is subtract MAVA prime from both sides and MBVB from both sides. So on the left, we have mass A, and on the right, mass B. We then factor out the mass on both sides, and we get this expression right here. For kinetic energy, we multiply the equation by 2, and we get this. And once again, we put A on the left side, B on the right side by subtracting it from both sides, and factor out once again the mass. Now, does this look familiar? We have the conservation of momentum over here, and here's our kinetic energy. This can be factored following this expression, right? A squared minus B squared is A plus B times A minus B. And let's show this. VA squared, that's this term. VA prime squared is this term. So we get MA times VA plus VA prime times VA minus VA prime. And on the right side, MB times VB prime plus VB times VB prime minus VB. The next step is to divide the conservation of kinetic energy, this equation, by the conservation of momentum equation, this one. You can check with your math teacher. This is okay. So here we go. We're dividing the conservation of kinetic energy by conservation of momentum. And what's canceling out here? This term and this term. And we're left with this equation here. One more step. We'll put the initial velocities on the left side again, and the final velocities on the right side. This is what we were looking for by solving these two equations simultaneously. Do you recognize the terms on the left and right of the equation? And what do they mean? The terms are the relative velocities of the two objects before and after the collision. It means that for all elastic collisions, independent of each other's mass, right? There's no mass in this equation. The magnitude of the relative velocity of the objects is the same before and after the collision. Consider two cars, one with velocity v1 and the other with velocity v2, as observed by a person sitting by the side of the road. The driver of either car will see the other car moving at a relative velocity of v1 minus v2. Using the conservation of kinetic energy and the conservation of momentum equations and solving them in a slightly different manner, where we don't get rid of the masses, the algebra is a little more intense, but not too bad. It might be fun to try. We wind up with these equations. Now, you're not going to be accountable for these equations on the AP exam, but it's going to show how certain elastic collisions work. So we have some nice symmetry here. Take a moment to compare the two equations. So you can pause the video, and when you're done, please move on. Using these equations, we will predict the motion of three specific cases and relate them to observation. First one, two equal mass particles collide. Second, a heavy particle collides with a light particle at rest. And 3, a light particle collides with a heavy particle at rest. For a collision of two particles of the same mass, m equals m1 equals m2. They have the same mass. When we make that substitution into the two equations on the left, and please go ahead and try that, they simplify. These two fairly long equations simplify to right here. VA prime equals VB and VB prime equals VA. This is telling us that in an elastic collision between two objects of identical masses, the two objects exchange velocities, occurring when two billiard balls strike each other. Another good example is found in nuclear reactor engineering. When uranium-235 fissions, it releases 3 high-speed neutrons. These neutrons are moving too fast to cause another uranium-235 nucleus to fission, so they have to be slowed down by colliding with another atom or molecule. What type of atoms would be of most use here? And just reviewing here a bit, here comes mass A with a velocity A, and its final velocity after the collision, this is an elastic collision, is going to equal the original velocity of this object, of object B. And V prime takes off, this one here, with the initial velocity that A had. So they exchange or switch velocities. So back to the nuclear fission, you would need an atom with a similar mass to the neutrons. A hydrogen atom moving slower than in velocities, slowing down, while operational reactors use water for this purpose. It's heavier than hydrogen, but has many other practical benefits. Nuclear engineering is not as simple as just analyzing elastic collisions. Now let's try a large mass striking a lighter mass at rest. So in this case, MA is going to be much greater than MB. That's seen over here. That double greater than sign means much greater. That means that MA plus or minus MB is roughly going to equal MA because MB is so small. So if we substitute those variables into these two equations, it simplifies to this. And it shows that the initial object that's very large roughly keeps its same velocity. However, the less massive object takes off with twice the initial velocity of the large object. So the velocity of the smaller mass after the collision will be about twice that of the more massive objects, while the more massive object's velocity will be almost unchanged. Picture a bowling ball striking a golf ball at rest. For this case, MB has a greater mass than MA, much greater. So MA plus or minus MB is approximately MB. This time the equations simplify to these two. So the heavy object barely moves, the large massive object doesn't move, and the lighter object hits with a velocity A and then keeps the same speed but in the opposite direction. So V prime A is going to equal minus V sub A. The large mass particle remains mostly at rest. The small particle reverses direction with the same magnitude as its initial velocity. Picture a moving golf ball hitting a stationary bowling ball. Example 1. Two objects, m sub A and m sub B, have an elastic collision. The initial velocity of MA is 8 meters per second and MB is minus 4 meters per second. After the collision, the velocity of MA is 5 meters per second. What is the velocity of MB? We weren't given the masses, but we were given 3 velocities. And since an elastic collision, we can use the relative velocity equation. So we substitute in our numbers and be very careful about the minus signs. We have 8 meters per second minus a minus 4 meter per second equals minus, and then the whole parentheses there, 5 meters per second minus VB prime. On the left side, we add those two, right? Because a minus and minus gives you a plus. And on the right side, be sure to carry that negative into the parentheses. So we have negative 5 meters per second plus VB prime. One more step, and we get VB prime is 17 meters per second.